Okay, so in the previous lecture, we got as far as discussing the first derivative test. So I'm going to review up to the first derivative test, and then we will see a few examples using the first derivative test. And then for functions where you're lucky enough also to have a second derivative, there's a second derivative test that you can use. Okay, so just to review, starting with global extrema. The global maximum of a function is the maximum element of its range, if it has one. And supposing that it has one, we say that f has a global maximum of f of x naught at x equals x naught. The maximum might occur at more than one point, right? The sine function would have maxima of 1 at infinitely many points if your domain was the reals, for example. Similarly, we said that for the global minimum, the minimum value of the range is the global minimum of the function. There may be one, there may not be one, depending upon the function and the domain. But if it has one, then we say that f of x naught has a global minimum of f of x naught as at x equals x naught. That's the terminology that is used. Okay, so for a global max, what we're saying is that you have a global max of f of x naught at x naught if f of x naught is bigger than or equal to f of x for every x in the domain of f. And similarly, for a global minimum, f of x naught on u, sorry, that's a misprint, on u at x naught, if f of x naught is less than or equal to f of x for all x in u. Okay, then we define local extrema. And there the idea was that if in some neighborhood, so you take your domain and then you intersect it with some open interval, and if on that intersection you have the values have a maximum or a minimum, then we speak of a local max or min. Okay. Right, so we did that before. We also defined increasing and decreasing functions. A function is increasing at a point x naught if the derivative at x naught is bigger than 0. The function f is said to be decreasing at x equals x naught if the derivative of f at x naught is less than 0. Then we would say that it's increasing on an interval, a to b, if the derivative is 0 everywhere on the interval. And it's decreasing on the interval from a to b if, again, that's another misprint, if the derivative of f of x, if the derivative f prime of x is less than 0 for all x on the interval from a to b. Okay. And the critical points were what? The critical points are the points in the domain of the function where the derivative is either 0 or the derivative does not exist. Okay, and in the theory we developed, it turns out that those points and the endpoints of the domain, if the domain has endpoints, those points are of interest in searching also for local maxima and for global maxima and minima. Okay, so the critical points are those points where the derivative is equal to 0 or the derivative of the function f does not exist. Those are the critical points of f. Okay, and we had this, last time we had this theorem that says if local extrema occur at x naught in an open interval where the function and its derivative are defined, then the derivative at x naught is equal to 0. So this doesn't mean that everywhere where the derivative is 0 you've got an extrema. What it means is if you've got a nicely behaved function, at least on those intervals where the function exists and its derivative exists, then out of the points where the derivatives are zero, some of those points are going to be the one. If they're a local extrema, that's where you want to go looking for them. Okay, now let's see what happens at a local maximum. Okay, so at a local maximum, the function is increasing. The derivative goes to zero, or it doesn't exist, and then the function is decreasing. Okay, so to the left of the critical point, the function is increasing. That means the derivative is greater than zero. At the critical point, the derivative is equal to zero, or it doesn't exist. And then to the right, the function is decreasing. The derivative is less than zero. And then right at the critical point, you have a local maximum. You have a similar story for a local minimum, right? So at the minimum, the derivative is zero, or it doesn't exist. To the left of that point, the function is decreasing. Then the derivative is zero, or it doesn't exist. And then the function is increasing. So if you have something like that, then you've got a local minimum. Right? So once again, let's remember, you could have, okay, so there's a question?
Yeah, sir, I wanted to ask that these local extrema, they occur at critical points only.
Yeah, if you have a function, or if you have, say, some subdomain of the function, you've got an open interval, then within that open interval, if the function exists everywhere on the open interval and the derivative exists everywhere on the open interval, then the local extrema will occur where the derivative is zero.
Okay.
But everywhere where the derivative is zero is not necessarily a local extrema.
Okay.
Okay, so that's why the extrema are candidates. The points at where the critical points are candidates for where the extrema are occurring, but they're not necessarily the points where the extrema are occurring. Okay, so in this one, remember, you've got a local minimum, which is also a global minimum at x is equal to 2, but the derivative doesn't exist there. The derivative is not equal to 0 there. It doesn't even exist there. Okay. Okay, so then we had the first derivative test. So supposing that f is continuous at a critical point, so that means the derivative is equal to 0 there. And like I said, to the left of the critical point, the function is decreasing. And to the right of the critical point, the function is increasing. Then at the critical point, where the derivative is equal to 0, the function has, sorry, no, sorry, okay, let me get this straight. The function is increasing. Then at the critical point, the derivative is 0. Then the function is decreasing. Then at the critical point, where the derivative is 0, the function has a local maximum. Okay, if you've got the opposite story, the function is decreasing, then the derivative is 0, then to the right, the function is increasing, then you've got a local minimum, or we also say relative minimum, at that critical point where the derivative is 0. Okay, now, if you've got a critical point and where the derivative is 0, and the sign of the function does not change to the left or to the right, right? As you go from left to right, the sign of the function does not change. The derivative remains positive, or the derivative remains negative. And then you've got neither a relative maximum nor a relative minimum at that point. Okay, so that's a review of what we did before. Okay, so now let's use the first derivative test to find some minima and maxima. Okay, so here's the function. F sends the closed interval from -5 to 1 to the reals, defined by f of x equals the absolute value of x. Okay, so where is the critical point here?
0.
You're right. At x equals 0, you've got a critical point where the derivative is not defined. Okay. Okay. So we call that a critical point. So now, if we've only got one critical point within the domain. Okay. So the intervals we're interested in are from the left end of the domain up to the critical point at 0. That's one interval from -5 to 0. And then we consider from the critical point 0 to the end, which is 1. Okay? So those are the 2 points of interest. Now, on the interval from -5 to 0, is the function increasing or decreasing?
Decreasing.
It's decreasing, right? You can just tell from the graph, right?
Decreasing.
It's decreasing. Now, from 0 to 1, what is it doing?
Increase.
It's increasing. So to the left of the critical point, decreasing. To the right of the critical point, increasing. So at the critical point, we have what?
Global minima.
We have a relative minimum by the first derivative test. Okay, right. So again, the derivative is -1. It's negative from -5 to 0. And then from 0 to 1, the derivative is +1. It's positive. Okay? So that means decreasing from -5 to 0 and increasing from 0 to 1. So that means you have a critical point. That means you have a relative minimum or a local minimum at x equals 0. And what is that local minimum? What is that minimal value? Well, f of 0 is equal to 0.
Sir, I had a question, sir. How did you figure out that on the left side it was decreasing just from that equation?
Well, on the left side, the function is f of x equals -x, right?
F of x equals to -x. Okay, sir.
Yeah.
And on the right side it's positive x. Okay.
Yeah. Okay. So now, if we're looking for, if we're also interested in global maxima and global minima, we should check the endpoints. So f of -5 equals 5 and f of 1 equals 1. So we've got a global max of 5 at x equals -5. And we have a local max of 1 at x equals 1. And we've got a local, which is also a global minimum of 0 at x equals 0. Okay? So if the function does have endpoints, be sure to check those also.
Sir, can you go a few slides back?
Yeah. You want me to go to the previous slide?
No, sir, a few slides back. The one with the function f is equal to absolute value of x.
Yeah, so we're going from -5 to 1, right? So if I check the endpoints, and f of -5 is 5 and f of 1 is equal to 1.
So why is the local maximum 1 and not 5?
Well, if you look at the graph, in the region around x is equal to 1, that's the biggest value, right? If you just take a small, if you take, say, if you go from 1 minus delta, where delta is something small, to 1, on that interval, the value 1 is the biggest value that you get. Okay? But the one at 5 is obviously bigger. So f of 1 is only a local maximum.
Sir, can you please repeat this point again? There's a lot of confusion in it.
Okay. When you go from 0 to 1, the function is increasing, yes?
Yes, sir.
Right? And so right at the endpoint 1, it has a value 1?
Right.
Yeah, so that's a local maximum. On the interval from 0 to 1.
Do we have to consider these? Do we have to consider these two as two separate, different instinct functions, or we are like considering it as a single range starting from -5 to 1?
All right, just a second. Let me pull up the graph. Okay, so hopefully you can see the graph. You see this value here at 5 is much higher than anything else. So it's a global maximum, right?
Right,
Over
sir.
here, on the interval, say from 0 to 1, the biggest value on the range is 1. So it's a
So this
local
is a
maximum.
local maximum. Right, sir.
Yeah. Okay.
And sir, at 0, we have global minimum.
Yeah,
and
it's a
local
global
minimum.
minimum as well as a local minimum.
Okay, sir.
Yeah.
It's understood, sir.
Okay.
Sir,
Thank you, sir.
can we say that 5 is also a local maximum?
Yes, sure. Because
Alright,
if you,
so
if
there
you,
are,
yeah, if you were to consider the interval from -4 to -5, the biggest value you have is there. So yeah.
all
There's
right.
another question?
Yes, sir.
Yeah.
So, why do we say that at 0 it's a global minimum, because it doesn't exist at 0 function?
No, the function exists at 0.
So isn't it undefined?
Absolute
Like
value of
there's,
0 is 0, so the function exists at 0. Yeah.
so but like when you plot it, like there's a gap when you put the pointer over there. Like there's no derivative for
Well,
that
there's no
either.
derivative, but the function still exists, right? I mean, the function is perfectly fine there. It just doesn't have a derivative there.
Okay, sir.
Okay. All right. Okay.
Sir, can I have a question? How is our local maximum 1 when you just said it can also be 5?
Okay. So let's go back here. Okay. All right. So if I go from say 0.9 to 1. Okay. So if I look at points that are close on an interval, which ends at 1, some small interval, say from 0.9 to 1.0, then the largest value of the range, if I'm just restricting myself to those values of the domain, the largest value that I get is 1. So that's a local maximum. Okay.
Sir, are you including the endpoint, the right one, right
Yeah,
endpoint?
the endpoint is in the range, right?
It's in the range, right?
Yeah.
Okay. Okay.
Now, if I go from, if I consider the entire domain, so when you're considering relative maxima and minima, you're only talking about pieces of the domain, a small part of the domain. But when you're talking about global, then you're talking about the maximal element in the entire range. So we can see from this graph that the maximum element in the range of this function, the maximum y value on this graph, is +5. So it's a global maximum, right? And the value 1 is only a local maximum.
Sir, is it safe to say that at point 0 is both the global and the local minimum?
Yes, it is. Yeah.
Okay.
Okay. All right. Okay, so let's consider, we considered this function before on all of the reals. Let's restrict ourselves from -3 to 3. So f of x is equal to x to the 4 over 4 minus x squared over 2. Okay, and here's the graph. Okay, then we can just see visually that from -2 to -1, the function values are decreasing. Then from -1 to 0, the function values are increasing. Then from 0 to 1, the function values are decreasing. And then from 1 to 2, the function values are increasing. So we would like to, the points that we would like to check are all the points where the derivative is equal to 0. And if we're looking for global extrema, we should also check the endpoints. Okay. Right. So as before, the derivative of this function is x cubed minus x. That's x times x minus 1 times x plus 1. And then we can see that the derivative will be equal to 0 when x is equal to 0, when x equals 1, or when x equals minus 1. So the critical points for this function are x equals minus 1, x equals 0, and x is equal to 1. Okay, there are no other critical points. So for the purposes of the first derivative test, the intervals that we're interested in, you want to go from the end point to the first critical point, which is minus 1. And then you want to go from minus 1 to the next critical point, which is 0. Then you want to go from that critical point to the next one, which is 1. So 0, the interval 0, 1. And then you want to go from, after 1, there are no more critical points, so you just want to go to the end of the interval. So you go from 1 to 3. These are the 4 intervals which are of interest, where you care about whether the function is increasing or decreasing. Okay? Well, all right. So on this first interval, is the function increasing or decreasing, right? So if you were to take a value between -3 and -1 and put it into the formula for the derivative, this formula over here, would you get a positive number or would you get a negative number?
A negative.
Okay. Okay, so if we put such a value into x, x minus 1 and x plus 1, well, when x is negative, x minus 1 will also be negative because you've got a negative number to the left of -1. And then the next one, x plus 1, it would still be negative. So the product of 3 negative numbers would be a negative number. So the function is decreasing on the interval from -3 to -1.
Yes, sir.
Okay. Now, the next interval of interest was from -1 to 0. If
Increasing.
if you put a number between -1 and 0 into x, x minus 1, and x plus 1, the first factor is negative, the next factor is negative, and the next factor is positive. So a negative times a negative times a positive will give you a positive number. And so that means that the function is increasing between -1 and 0. Okay, the next interval of interest was 0 to 1. Now, if you take a number in there and you put it into x, it'll be positive. If you put it into x minus 1, the result will be negative. And if you put it into x plus 1, the result will be positive. So positive times a negative times a positive will be negative. And that means that the function is decreasing between 0 and 1. The final interval of interest was 1 to 3. Now, if you take numbers between 1 and 3, and you put them into x times x minus 1 times x plus 1, in the first factor, you'll have a positive number. In the next one, you'll have a positive number. And in the third one, you'll have a positive number. The product of 3 positive numbers is positive. So the function is increasing between 1 and 3. Okay. All right. So let's apply the first derivative test at x is equal to -1. Okay. So let's go back here. So at x is equal to -1, the function was decreasing between -3 and -1. Then the function was increasing from -1 to 0. and the derivative was 0 at x is equal to -1. So what do I have?
Local minimum.
Local minimum.
Local.
Okay. The function was increasing between -1 and 0.
Sir, can you again explain this local minimum thing? Just what you just said.
Yeah. If the function is decreasing on the interval to the left of the critical point, and it's increasing in the function to the right of the critical point, then at the critical point, you have a local minimum. Okay?
Okay, sir. Okay, sir.
So in this one, the function was increasing, the derivative is positive between -1 and 0. And then we said that the derivative is decreasing between 0 and 1. And right at 0, you had the derivative was 0, right? So what do we have here?
Local maximum.
We have a local maximum. Okay. Now, here we had the function, the derivative is negative. The function is decreasing between 0 and 1. The derivative is 0 at 1. And then the function is increasing from 1 to 3. So by the first derivative test, the function has a local minimum at x equals 1. Okay. Okay. So we determined that there was a local minimum or a relative minimum at x is equal to -1. We want to know what that is. We put in f of -1. We get -1/4. So we say that there's a relative minimum of -1/4 at x equals -1.
Sir,
Yes.
Sir, if you put this -1 into x over 4, so shouldn't it be -1 over 4? But over here it's written 1/4.
No, it's x to the 4th, right? So -1 to the 4th will be 1.
Okay, sir.
Okay. So now we said that there was a relative or a local max at x is equal to 0. So we report the result like this. There's a relative max of f of 0 equals 0 at x is equal to 0. Then we said that the first derivative test gives us a relative or a local minimum at x equals +1. So we report a relative minimum of f of at +1 is equal to -1/4 at x is equal to +1. Okay. Now we test the endpoints. F of -3 gives us 15.75, and f of 3 gives us 15.75. Notice that these are greater than the local max that was reported. Okay, it was a local max of 0. But we've got values at the endpoint that are greater than that. Okay, so that means that when we compare to the, I mean, it's possible that some of the local maxes could be global maxes also, right? But in this case, it's not the case. So we get a global max of 15.75 at x equals ±3. Okay. All right, so are there any questions about that one?
Sir, but in reality, we have a global max at x is equal to -5.
No, but I restricted the.
Oh, okay. You are talking about an interval. Okay, got
Sir,
it.
what is going to be our global minimum?
What's the global minimum? Yeah, the global minimum. When we look at the local minima, we had a local minimum of -1/4 at +1, and we had a local minimum of -1/4 at -1, And then we tested the endpoints and we didn't get anything that was smaller than that. So in this case, the local minima are also the global minima of the function. Okay. Okay. So we would say that there are global minima of -1/4 at x is equal to plus or minus 1 for this function. Okay. Are there any other questions? Okay. So now we come to the second derivative test. And if you have a function which is twice differentiable everywhere on its domain, then you can use the second derivative test, right? For say the absolute, this thing we did with the absolute value function from -5 to 1, it doesn't have a second derivative. It doesn't even have a first derivative, right? So the second derivative test doesn't work for such a function. Okay, but let's suppose that you're lucky and you do have, it's twice differentiable. So you have a critical point x0 where the derivative is equal to 0, and at the same time the second derivative at that critical point x0 is greater than 0. That means, so the second derivative test says that you have a local minimum at that point. Okay? On the other hand, if you've got a critical point where the derivative is equal to 0, and the second derivative exists at the same point, at the critical point, and is less than 0, that means you've got a local max at x0. Okay? And then the other thing that could happen is that you've got a critical point x0 where the derivative is equal to 0, and the second derivative also exists at the critical point, and it's also equal to 0. Then that's neither a local max nor a local min, and it's a point of inflection at x0. Okay.
So what is the point of inflection, by the way?
If you look at the graph, it's going to be either concave up or concave down, and it's where the concavity is changing. Second derivatives are a measure of curvature. Okay.
Okay.
So the curvature is changing. All right. So let's say that I've got this function, and let's say it was for all of the reals, defined on all of the reals. So the function is x to the 4 over 4 minus x squared over 2. I take its second derivative, its first derivative is x cubed minus x. Then its critical points are -1, 0, and 1. We already did all of that, right? Now, yes, someone has a question? Hanya?
Yeah, so what could you repeat what you said about functions that don't have a second derivative?
Oh, okay. So this function, we had the absolute value function, right? So at x equals 0, you have a critical point with it, even the first derivative doesn't exist.
Yes.
Right? And then the second derivative doesn't exist. And so you can't use something like the second derivative test for.
Oh, so you just can't use the test on those functions?
Yeah, you can't use this test on those functions, yes.
All right, thank you.
Okay, so, right, as before, -1, 0, and 1 are the critical points. So when we applied the test, the second derivative, so the first derivative is x cubed minus x. The second derivative is 3x squared minus 1. Okay? So now, if I plug in the second derivative at the critical point -1, I get that the second derivative is equal to 2, which is greater than 0. So the first derivative is 0, the second derivative is positive, the second derivative test says that you have a minimum there. Okay? At +1, the first derivative is 0 at +1. The second derivative is positive at +1. And so the second derivative test says that you have a minimum there. Okay? And at 0, the first derivative is 0, the second derivative is negative, and so you have a local maximum at that point.
So, sir, sorry, sir, can I ask a question?
Yes?
Sir, just like we were looking at the graph and we were like pictorially like determining whether it's a minimum or a maximum using those lines. Now,
Well,
by doing the second,
we didn't need the graph. We used the first derivative test.
yeah,
Yeah.
yeah, sir. So if we take the second derivative, we will be able to judge whether it's maximum or minimum, global maximum or global minimum.
Yes.
Am I right?
No, a local maximum or a local minimum.
So it doesn't apply on the maximum, global maximum and minimum.
No, what
right?
you do is you get your local maxima and you get your local minima and you calculate at the endpoints, and then you look through the values that you got and you see which one.
Oh,
right.
Right.
Okay.
Yeah, right, sir. Thank you.
Right, because at the endpoints, you may not be able to apply this. You know, the first derivative may not be 0 at the endpoints, right? So the endpoints
Yes,
have to be considered separately. Okay.
Oh, okay, sir. Thank you.
Okay. All right. So now, let's say I have f of x is equal to x cubed. Okay. So the first derivative is 3x squared. That's 0 at x is equal to 0.
6.
So there's one critical point,
6.
right? And
Yes, sir.
the second derivative is 6x. And 6x is also equal to 0 at x is equal to 0. So the second derivative test says that this is a point of inflection.
Yes, it's not maximum, nor is it minimum.
Yeah, this function has no maximum and it has no global maximum, it has no global minimum. It doesn't even have a local max or a local minimum.
It's a point of influx.
Yeah, that's called a point of inflection at x equals 0.
Thank you, sir.
Okay.
Sir?
Yes.
I had a question.
Yeah.
So how is this point represented on a graph? What is it shaped like?
Oh, okay. Let's take a look.
It's just like a logarithmic function after 0, x is equal to 0, increasing and increasing and increasing. And if we go to the left side of the x is equal to 0, it's decreasing and decreasing continuously with an increasing rate, since it's cubic. -1, 2.1.
Okay, so if you take a look,
Yes, sir.
It looks something like this, right? And so at such a point, you see that the concavity is changing.
And so as we like increase the range, like we did it from -0.1 to 0.1, if we increase that from -2 or -3 to 3, then it will like shift towards the y-axis. This concavity will increase.
Well, I mean, we're only concerned about what happens at the critical points in this case, right? So this function is simply increasing as you go along, right? Because 3x squared is always non-negative, right?
Yes, sir.
So,
Sir?
yeah. Yes?
Yeah, go ahead, sir.
Yeah, so as you go from left to right, the values that you get are simply increasing, right? And since we've defined it from -infinity to +infinity, it has no local max, no local min, no global max, no global min.
Sir, so the point of influx is when the coordinate axis is changed.
Yeah, the point of inflection, it has a point of inflection at x equals 0, and that's where if you want to think about it geometrically, that's where the concavity of the function is changing.
And sir, how do we find a global maximum using the second derivative
Maximum.
test?
Okay. Find the local max and mins. Then if there are endpoints to the function, test at the endpoints. And then from all of those values, all the function values at those points. So the function values at the critical points and the function values at the endpoints. Look at those and see which one is giving you the biggest one. That'll give you your
So
global.
0.0 and negative 0.10 is giving you the greatest points.
Well, okay, but I've just drawn a part of the graph. The way we defined this function, it was going from the reals to the reals. But yeah, if we defined it this way, that it was going, the domain was minus 0.1 to plus 0.1, then there would be a global max at 0.1, and there would be a global min at minus 0.1.
Sir, but this cubic graph, does this have a max or min function? Because doesn't it have an asymptote as we increase?
Yeah, I was saying if we made the domain some finite interval, right? Then it would have a finite closed interval, right? From A to B, including A and including B. Then you could find a global min or a global max. If you have an open interval from A to B, not including A and not including B, then there will be no max or min of any kind.
I think, sir, that this particular graph, whatever number you take, it won't be like at like an asymptote, that vertical asymptote won't be formed. Yes, it's true that it's approaching towards that situation, but it will never be formed.
Okay.
Whatever way.
Yeah. Okay.
Sir, I had a question.
Yeah.
Go on.
Sir, but in this graph, even if we finite it to a finite interval, but there isn't any point in the graph where the differential is 0. So how do we
right.
say that it's a maxima or minima?
Oh, but there'll be a global, there'll be a largest value, right? If I said f of x equals x cubed from 0 to 10, including 0 and 10, then the maximum value is 10 cubed equals 1000, right? Right? Global max means the largest value in the range of the function, which doesn't necessarily happen where the derivative is equal to 0.
Oh, okay.
Sir, I had a question.
Yeah.
Sir, if when finding out basically the global and the local maxima, we'll first take care of the critical points, then the endpoints, and then put after finding those, we'll put it in the function. And the highest value would give us the global maxima and the global minima out of these candidates, and the rest of them would be local maxima and minima, right?
Yes. Yes.
And sir, the second derivative test only applies to local maxima and minima.
Well, yeah, the second derivative test applies to functions where you have critical points, where the derivative is 0. Right.
So, sir,
it doesn't apply to points where the derivative is not defined.
Like the purpose of doing the first derivative is like judging out if it's greater than 0, it's an increasing function, less than 0, it's a decreasing function. When it reaches 2 equal to 0, then that is the point where we apply the second derivative in order to find the local.
Well, I mean, if it's a nicely behaved function like a polynomial, then taking second derivatives is possible, and you can apply the second derivative test. When you've got functions that have these corners in them, where the derivative is not defined, then you can't apply a second derivative test to it, right?
Mm-hmm. Right, sir.
Okay.
Oh, sir, I want.
So, please.
Okay, sir. In the absolute function, in the slide number 28, sir, how did you figure out without looking at the graph that from -1 to 0 it was an decreasing function, and from 0 to 1 it was an increasing function?
Oh,
I guess it was slide number 88.
Well, okay. So the way the function is defined, we said before that f of x equals minus x for negative x values, and it's equal to plus x for positive x values. So the derivative of minus x is -1. and the derivative of plus x is plus 1.
It's answer 28, I guess.
That's what I would do. Okay.
Yeah, so this one.
Yeah, so the derivative is minus 1 to the left of the critical point.
So
Right.
how did you, without looking at the graph, how can you figure this out?
Okay.
fx दिया हुआ था ना modulus है वो.
F of x is equal to minus x for negative x, and f of x is equal to plus x for positive x.
Oh, okay, sir. Okay.
Yeah.
Sir, are the rest fit to leave?
Well, yeah, I mean, that's the end of the lecture. I'll stick around.
So are we done with extremas?
What?
Are we done with extremas?
Yeah, we're finished with the discussion of extrema.
So we are done with midterm syllabus, right?
Yeah.
Okay.
Any last point advice you have for us for preparing for our midterm exam?
Yeah, do the homework. Do the homework seriously.
Okay.
I mean,
okay.
Not looking at Wolfram Alpha, not accessing your friends. Do the homework seriously.
Sir, can you briefly describe the paper pattern? Like, will it just consist of MCQs?
No, it's all of us are going to get together and make questions, so it could be anything.
No, a brief like layout of the question paper. Like,
But
will
like
it
I
just
said,
contain?
all the instructors are going to be contributing to this, so anybody could come up with anything. I don't know what the other people are going to do.
Sir, okay, that's fine. Sir, but what do you like? We are not talking about other instructors. We are talking about you. What do you think that what should be in the midterm exam? Maybe you will be able to convince them up.
No, I mean, there's likely going to be a mix of different types of questions. Some MCQs, some questions where you have to work things out, right?
Okay, sir. What we wanted to know, we got it.
Okay.
We have to upload the workings or something like that.
Probably.
Okay, and anything like a graph.
Yeah,
like graphs and all.
I suppose if we ask you to
to
draw a graph, then we'd ask you to take a picture and make a PDF or something.
So what would be the time for the exam on Saturday?
I don't know. It could be between.
I guess it's 2 hours.
It could be.
Try not to
It
do
could be 1
graph.
to 2 hours. Yeah.
Sir, I also agree, if possible. Could you maybe contribute this idea while making the questions to not include too many graphs? Because plotting the graphs on a plotting software and then taking a picture and
Yes,
then
it's really
uploading.
hectic. It's really time consuming, to be honest.
Yeah.
Sir, I have a question.
Yeah.
So will we have
Sir, what will we do in the next class on Thursday?
Mean value theorem.
Is it coming in exam?
Yeah, the mean value theorem is the next. No, mean value theorem I don't think is on the exam.
Okay.
Anyways, I mailed you the syllabus, so that's whatever was there was on the exam.
So by the way, I did send you a question of limits. Can you just briefly describe its working? On email.
Yeah, the limit that you are given
The sign one.
is a derivative.
No, do we have to use like L'Hopital rule or?
No,
Like,
it just takes a derivative.
so we have to take derivative.
Yeah, take the derivative of that function at 0.
Okay, thanks sir.
टेस्ट वेबवर्क पे होगा या एनी क्लू लाइक
Okay, there's another question?
टेस्ट जो है वो वेबवर्क पे होगा या लाइक
I don't know yet.
that
So will we have to give the proofs, the working for the proofs?
You mean no? I think you just copied them out of your book if we ask you that.
Okay, thank you, sir. Allah Hafiz.
Allah Hafiz, sir.
Right.
Sir?
Sir? Yes?